Welcome to this GXC Research Vision webinar series. This is third one of those. And this webinar is about white paper on connectivity for remote areas. And I like to thank the whole group of that white paper for this. We will show the results of the white paper here. So today we will have a very interesting and exciting presentation about these remote area connectivity problems. My name is Harri Saarni. I led the writing team, and I come from University of Oulu, and I will give this introduction, some practical things, and then talk about some numerical facts what we have collected. Then Alok Pandey talks about regulatory and proliferation challenges, especially in India. Then Mohamed-Slim Alouini talk about wireless backhaul solutions. Then Brejesh Lall talk about elasticity in radio access net solutions. Then Abdelaali Chaoub talk about spectrum usage, what we can do there. And finally, Adrian Kliks talk about the regulation aspects. Okay, we don't take live questions in this time. So please, if you have questions, write them into QA window. And then after last presentation, we will answer them. And maybe we'll also answer written to all these questions, but that will be seen. And we will record this webinar, and you can find the video afterwards from the GXC webpage. And we are also in social media. You can see these tags there. So what kind of facts we have collected? So about half of the population in this globe live in the rural areas and half do not. 2/3 of people have mobile broadband subscription, so cellular phones mainly, but only half of the people have internet connection. And of those who don't, they live in rural and remote areas. Urban area, that is one digital divide. Then there is second digital divide is the data rate. So in rural areas, urban areas, we often have 100 megabits per second or even more. But in rural areas, we go down to 1 megabits per second or even less in some parts. They are still relying on GSM phones. And then there is also one problem because the service providers say that there is coverage in this area, but still the quality of service is very poor. You cannot not really use your phone, at least indoors. You have to go outdoors in the specific spot to get connection. So there is digital divide and it's getting even worse. What are the challenges what we are talking today? There is some low income areas in the rural places, low population density, lack of infrastructure like power grids, roads, and so on. There are difficult terrain which makes building the infrastructure and connections very expensive and less attractive to operators. The goal is that the service will be affordable and sufficient for all. And what we mean sufficient is that we mean that it's what we have in today's cities. There is not just technical problems to solve this connectivity, but also regulatory and operational problems. This will be talked more later on. I will don't touch those. So as a summary in GXC, we should look solutions for these challenges, and there are many, many more challenges what we have to solve. So I will ask Alok to give his presentation.
Good evening, everyone. Am I audible?
Yes.
Thank you. At the outset, I would like to take this opportunity to thank Harry and my esteemed co-panelists to provide me this opportunity to present my thoughts on the regulatory and proliferation challenges associated with 6G. I would frequently fall back on my experience with the Indian telecom industry to highlight the challenges that lie ahead. Why I feel it convenient to cite the Indian context, I believe and maintain that it is particularly important to get a direct insight into the market dynamics of a country that houses 1/6 of the world's population. It is the second largest market in telecom, next only to China, has 1.2 billion mobile subscribers, offers free voice calling services, and a data at an abysmal price of zero point zero 0.09 GB, $0.09 per GB, and has the highest per capita monthly usage of data in the entire world as on today. So that makes India a very lucrative destination to be studied. While these are the parameters on which we are evaluating 6G, and I leave it, and I'm sure this will be covered in far more detail by the technical panelists. I would focus myself on the regulatory aspects of the 6G evolution. The regulator has a very difficult task of balancing the industry's growth and interest vis-a-vis the consumer's interest. It is only natural that whenever a new technology is on the horizon, the regulator is faced with the dilemma of regulating it either ex ante or ex post. It has been the effort of the regulator world over to let forces play out, market forces play out, and attain a sustainable equilibrium. Once the technologies like 6G come into picture, these are extension of previous generations of telecom technologies. So it is very tempting for regulators to try and address the unaddressed questions of the previous generations X and in a forthcoming generation. Specific to 6G, let's see what the regulator's maze looks like. So you will see over here that the enabling technologies that work towards ensuring a conducive regulatory policy framework is essential for delivering of the desired application. The regulator have to deal with issues like spectrum, AI, and energy efficiency. With telecom becoming the enabling tech infrastructure for almost all business in the world today, regulatory actions have an overarching effect on business verticals across the world. The enabling features of 6G, that is distributed AI, real-time intelligent edge, intelligent radios for 3D integrated communication, now force the conventional regulator to step out of the comfort zone and holistically look at 6G as a service where data protection, digital privacy, and quality of service are of paramount importance. Having seen the regulatory complexity, let us now dwell upon each of the challenges one by one. Some of the challenges that are very apparent and which came to my mind, I've listed them down over here. The first challenge is quality of service. Given the fact that 6G emerges as an enabling infrastructure for business verticals like medicine, commerce, autonomous transportation, and holographic communications, it is essential that it meets the quality of service parameters in terms of reliability, availability, and service-specific throughput assurances. The reliability of 99.99999% has to be measurable, and mechanisms for the same need to be evolved degree of fiberization. One of the most important facets for ensuring the 99.9999% of the Q of the reliability that we are talking about. There is a significant variation in the fiberization across the world. While countries like the US, Japan, China have 70 to 80% fiberization, countries like India and other developing countries have it at just about 20%. Right of way. It has been an Achilles heel for the regulator and the telecom service providers. Despite the best intentions on the issue, the right of way remains a challenge. It has been my personal observation as a regulator that various municipal bodies, state and central administrative entities treat ROW as a source of revenue. And therefore, there is a need to standardize the charges admissible on a common set of evaluation parameters. It may be prudent to have a single window system with associated deadlines for according ROW. This, I say, particularly is relevant in the Indian context, where certain ROWs are accorded once in a year, like the Ministry of Forest. This has severe implications in commercialization of service by the network operators. Spectrum availability. While ITU is yet to finalize the proposed spectrum bands to be used for 6G, it is envisaged that the spectrum would be required across bands, besides the terahertz band that has been identified. Availability of the desired bandwidth in these spectrums, which are already being used for 2, 3, 4, and 5G services, remains circumspect. And if at all it is available, it is highly fragmented. The regulators must therefore embark upon an exercise of harmonization of the existing band allocations which has already been made. Spectrum pricing has always been a subject of active debate globally. Availability of spectrum by itself is not enough. The licensing and pricing has to be done in a manner that is economically viable for the MNOs to provide the 6G services. I will touch upon the commercial aspects of this pricing of spectrum when I come upon the challenges which are associated with its absorption. Tariff regulation. Tariff has been used as an important lever of regulation by all regulators, especially in case of emerging technologies. It is important that the regulators let the market forces play out during the infancy and use tariff as a regulatory mechanism only if it reaches a stage of mass adoption and potential emergence of monopolies. Issues with respect to digital protection and privacy, since data is going to be the key element enabling decision making and service delivery in the 6G era, data sanctity and safeguards against unauthorized data sharing, processing, cross-border flow of data, and data corruption needs to be in place. It is envisaged that the existing data protection framework like the GDPR would also need to undergo changes in the 6G era, as notice and consent would translate to consent and notice in a M2M environment, which is much different than what it is between a M2C environment. Cybersecurity, end-to-end security in terms of application security, device security, and network security needs to be built in as a design in the 6G infrastructure. The regulator would need to evolve a methodology to be able to assess the compliance of 6G infrastructure on parameters of confidentiality, integrity, authentication, and encryption. Any lapse in these would have potentially catastrophic impact across industry sectors. Legal liability. This challenge can best be amplified through an example in the envisaged 6G autonomous transportation era. Let us for a second assume the failure in quality of service parameters due to an intrusion, breach of security, or faulty decision making due to lack of adequate data protection, leading to an inadvertent accident. who will be held responsible for the loss of life and property as a result of this accident? The vehicle manufacturer, the service provider, or the owner of the vehicle? In a different scenario, just imagine yourself to be on the operation table being operated remotely by a surgeon, and such a lapse takes place. Therefore, it is very important that legal liability be clearly demarcated amongst all stakeholders. Environmental impact as analysis. Network densification would lead to substantial increase in the number of access points and the BTSs. These access points would not only be in the two-dimensional space, but will also be in the third-dimensional space and would have to be lit up, which have associated implication in terms of carbon footprints and e-wastes. Regulators will have to be proactive in defining the pollution control compliances and enable the device ecosystem manufacturers to adhere to them. The debate between hazardous effect of radiation from telecom services has been going on for quite some time now and is likely to intensify in the increased BTSs and access point environment. Therefore, the regulations in terms of peak power outputs and permissible areas of use will have to be again put in place, which are a challenge in themselves. I would like to highlight in this particular case that Indian courts have gone to the extent of ordering shutting down of 2G BTSs, treating them as possibly carcinogenic. So 6G service providers are in for a big challenge up there. I will now analyze the service providers' perspective. This is very important in the light of the fact that researchers should be mindful that every research is oriented towards a business goal. And the aim of all business is, as a thumb of rule, is to generate profits. For providing any service, the service provider invariably needs access to infrastructure and resources, both of which could either be owned or leased, and therefore translate into investment in the form of CAPEX and OPEX. Developing a telecom infrastructure is very capital intensive. To put it in perspective, India has 2.1 million BTSs, 1.4 million kilometers of optical fiber cable for servicing its 1.2 billion subscribers. But the level of fiberization is at an abysmal 20%. The Cellular Operator Association of India estimates that approximately 23 trillion Indian rupees, which is about 230 billion US dollars, would be required to achieve a fiberization of 70% of the existing BTSs, which are essential only for the rollout of 5G services, and that too in pockets. Besides fiberization, the access is dependent on the availability of spectrum. As I brought out earlier, the spectrum comes with its associated financials. The reserve price of the 8,300 megahertz of spectrum, which is likely to be auctioned very soon in India, has been pegged at approximately $75 billion, which is roughly 900 euros per slot, per spectrum slot. This approximate cost of about total aggregate approximate cost of $350 billion is exclusive of the associated OPEX, taxes, regulatory compliances. Contrast this with the revenues of almost $1 ARPU earned per month.
Alok, can you go to conclusions? Time is running.
I would just take 2 more minutes. I'll just finish it off. Not surprisingly, of the 12 to 14 odd MNOs who were contending for the market share in India have been reduced to just 4 MNOs. I would skip the portion of the issue related to the availability of data at much cheaper prices. However, if you see the ARPU in the Indian context is, while it is approximately $2 per operator, the average ARPU is just $1 in India. 6G, like any other new product being or service being offered, will have to go through its Gartner's hype cycle, where there'll be a lot of contention in the field of standardization in the initial stages. And as things standardize, there'll be few stable players to survive the market. And concurrently, you'll see the market forces play out for 5G and 6G S curves. And the basic challenge would be determination when to jump the S curve from 5G to 6G. As per the envisaged timelines right now, it will be somewhere around 8 years from today. And therefore, at present stage, we need to be very aware of the fact that we need to research on a very broad base. And as we reach closer to the time to market, we should focus on deliverable technologies. Talking of deliverable technologies, it is very important that we take into consideration that each use case that is developed through the research and development process funded by developed world need not necessarily be meeting the requirements of a developing or underdeveloped country. A classical example on this is the low mobility large cell concept, which was accepted as a 5G standard. So therefore, in this particular state, at this present state where research is on in the field of developing of standards and standardization, we should be mindful and be inclusive of the developing and the underdeveloped world's requirements also. I have finished. Sorry about overshooting by about 2 to 3 minutes.
Okay, thank you for these insights to these interesting challenges what we will face in the future. Now the next speaker is Mohamed-Slim Alouini. Are you there, Slim? You can share your screen.
Yes, yes. Thank you, Harry. Let me put my screen in full mode. Okay. Thank you again, Harry, for organizing this webinar and for giving me the opportunity to talk on behalf of my colleague that were in this task force, focusing on basically wireless backhaul and more specifically non-terrestrial networks. So this work involved Marco Giordani, myself as editor of this part in the white paper, and contribution from the colleague that you see listed here. So obviously, if you look at this map, and as a follow-up on what was already mentioned, and this map is basically showing the current worldwide 4G distribution, it's clear that we are suffering from serious gaps in global internet connectivity, which is one important concept, concern, sorry, for 4G, even 5G. We tend indeed to forget that about half of the world population, somewhere between 3 to 4 billion people, are either kind of not connected or underconnected. And actually, it's expected that 5G in its current initial deployment will further accentuate this connectivity divide. So that's why we have this task force trying to basically connect remote areas and connect the unconnected. So basically, we can see all the benefits for all people on the planet. So the question is, why is it so difficult? Why are we having these bad statistics? And this can be explained by looking at this diagram. So when you look at this diagram, you can see that traditional geostationary satellite communication system, which are, of course, as you know, great for TV broadcasting, but they kind of offer limited bandwidth and suffer from a high latency as far as internet browsing is concerned. So they cannot deliver fiber quality for the kind of objective that we have in terms of broadband internet delivery. So the same diagram here in front of you illustrates that full deployment of fiber cables or microwave wireless link is not really economically feasible for remote rural areas, which are typically characterized by a low density of population. So I would say that our goal should be to go after this global connectivity holy grail on the top left of the diagram displayed in front of you. And here we need to go for the best of both worlds, targeting a terrestrial fiber quality, but with a global satellite coverage, hopefully fulfilling this interesting kind of prediction made 100 years ago by Nikola Tesla, and that you can all read in front of you. So this is the problem, and this is the objective. And the question is, how can we do that? So to do that, we need essentially to rely on the so-called 3D networks, or integrated space, air, ground networks. So essentially, the idea is to rely on the deployment of these three layers. And this is to avoid kind of deploying costly infrastructure just on the ground. So the idea is flying network platforms such as UAVs, tether aerostat or blimps, high altitude platforms, as well as satellite, of course, can all help in this matter. So like there is quite a bit of research going on these days on how to integrate satellite, airborne, and terrestrial network, and that are basically aiming to support both these remote and rural areas. And the idea that these kind of networks will rely on, of course, still terrestrial base station, but also these drone, balloon, HAPS satellites. And these kind of different layers will adapt their structure and the resource allocation based on the ground population density and based on the quality of service requirement by the kind of applications that are going to be used by the population on the ground. So when we talk about kind of connecting remote areas, the problem of backhaul is actually a primary problem, because you need to kind of do it in an aerial fashion. And obviously, the classical way of doing that is through satellites. Satellite offer a robust channel for backhauling operation, and thereby saving a lot of, let's say, terrestrial resources for long-haul traffic demands. The good news is recently we have seen kind of a drop in the cost of manufacturing satellite, which allowed mass production. And there are a lot of nice, interesting projects going on now worldwide, according to different satellite kind of families or technologies. There are people who are focusing on very high throughput satellite. There are people or like research or development being also focused on the so-called mini like geo satellites. And also there is a lot of interesting project. You can even call it a race between different giants like SpaceX with the Starlink kind of constellation, or the Amazon with the Kuiper constellation, trying to kind of launch these 100, if not 1,000 satellite to bring these backhaul capabilities. So one example, as I just to illustrate here, is like this concept of next generation hybrid very high throughput satellite that can carry up to 1 terabit per second. On one side, they will have the user link part, which will have all these kind of beamforming capabilities to follow traffic condition on the ground. On the other side, the feeder link, kind of to kind of address the issue of spectrum scarcity, maybe using kind of free space optics, and with multiple optical gateway station on the ground for site diversity purpose to avoid clouds. So this is like one direction that can help bringing kind of a robust backhaul to remote areas and connect them to basically broadband internet. Now, once you secure basically the backhaul, you need, of course, to complement that by kind of an access solution. Now, typically, for example, what is being used is once you land somewhere, you can kind of capitalize on TV towers to create these kind of macro cells of tens of kilometers to distribute or give access to internet in these remote areas. Now, these TV towers typically are on the top of hills or mountains, but they can be quite costly. Now, if you end up living in an environment where it's more flat, if you don't have a TV tower, if it's kind of expensive to use these TV towers, you can rely on these kind of emerging new solutions that are based on UAV or balloons, and in particular tether UAV that have the advantage of essentially having a very long lifetime in comparison to the UAV that are basically tetherless and that have a limited flight time of 1 hour or so. As soon as you tether them, you give them power and you can allow them to fly for multiple hours, if not multiple days, and some of them actually multiple weeks. And actually, you can also give them data through a fiber optic insert in the tether and connect them to the network that way. And the backhaul can be done, for example, through a satellite dish on the top of a track that is acting as a ground station for this tether UAV. Now, a tether UAV can give you a coverage of about 30 kilometers or so of a radius. If you want to push this kind of concept even further, you can go to these tether balloons. There are multiple companies in the US who are kind of active in this area. And we are talking about balloons that can be, again, attached to the ground at an altitude of 500 meters all the way to 1 kilometer, and with a radius that can go up to 1 kilometer, to 100 kilometers. So like really a macro cell that can give coverage to remote area with a very sparse population. And again, the tether can have power and can have fiber that connects this balloon to, like let's say, a satellite backhaul or to a fiber backhaul if it happens to be in an area connect to a fiber. Now, one extra step, or if you will, if you want to go one further up and get maybe like a larger coverage area, you can go for the so-called high altitude platform that are also picking up quite nicely in many kind of projects. You have Google who launched this Loon project, and that was kind of that's actually already providing internet in the remote areas of Peru and of Kenya. There is Zephyr, who has this project called, it is an Airbus project called Zephyr, which is kind of also kind of advocating for this high altitude platform. Essentially, we are talking here about flying a base station at 20 kilometer altitude in the stratosphere above weather, above climate. And you can basically rely on many of them being interconnected together to cover a large area. And again, one mother, let's say UAV, can be acting as a feeder, can has a feeder link to the ground that can be backhauled through a satellite. So this is kind of an overview of the different kind of space and aerial solution that are being investigated and that are being pursued to connect this remote and low density population. And I think there is quite a bit of interesting research that still has to be done to make these actually a reality and to see many of them being deployed to connect the remaining unconnected 3 to 4 billion people. With that, I would like to thank you for attending our webinar. And again, I would like to reflect a little bit on this interesting other prediction made by Nikola Tesla about 100 years ago about how he sees the world as a fully connected kind of world. And this is hopefully what we'll be able to achieve by the launch of 6G in 10 years from now. Thank you.
Okay, thank you for this overview. Brejesh, floor is yours. And our audience, please don't be shy with the questions. There is lots of room for those.
Thank you, Hari. Thank you very much for providing me this opportunity to talk very briefly about one of the aspects of providing connectivity to remote areas, namely how do we do it using a more elastic band. So I this went into for some reason slide mode and it started changing slides by itself. So give me a minute. So essentially what we're trying to do here is that over the last few years, the way the radio access network has evolved is that the number of halls or hops that it takes to reach from the core to the final user equipment has increased over time. So we will try to understand how can we address how can we leverage this change in technology to address one of the most fundamental issues in providing connectivity to a remote area. So the biggest problem to providing connectivity to the remote area is that the providers are extremely averse to investing either for spectrum or for infrastructure in these areas. the primary reason, of course, is that the return on investment is poor for various reasons. But the implication of all of this is that as the telecom services evolve from 2G to 5G and beyond towards 6G is what we're talking about right now, a section of the users are, well, are sort of ignored because of the poor return of investment. And now what we're trying to say here is that evolution of RAN over the last few generations offers an opportunity that can be leveraged, and it can be effectively adapted to mitigate this issue. And that is what I'm going to talk about in the next few minutes. So what we've noticed is that over the generations of telecom standards, when you talked about connecting the user equipment to the network, you only had a single air interface, and then you had the BTSs, BSEs connected to the core. But as the evolution continued, what happened was that you started talking about a front hall where you had a baseband unit and a radio unit, the two connected using the front hall. As time progressed, people talked about splitting the baseband unit up also into the centralized unit and the distributed unit. And recently, there's also talk of splitting the radio part further into the radio unit and the antenna unit. And if you look at this figure that I show here, there are further multiple ways of splitting up each of the units. So the point in matter is that the connection from the core to the final end equipment goes through multiple halls, and each one of them now can be designed in a manner that it can actually mitigate the problem for connecting the rural networks rather than making it even more challenging. There are two drivers to this. One is that because of this advent of AI and ML, it has become possible to handle a large number of resources at the same time. So on the one hand, having this kind of a split in the RAN makes it, makes it important to handle a large number of network elements. But AI ML is a very useful tool to achieve these kind of capabilities. So this is one driver that can help us achieve the goal. The other driver, of course, is that a lot of network function capabilities are moving to software. So you can pick up a generic hardware and on top of it write software in a manner that you want to implement. So now what happens is that you have on the one hand a cost disadvantage, which is making people not look at remote markets all that carefully. On the other hand, you're having this RAN being split up into multiple number of elements, and there is a large amount of flexibility in how you split it. And this has now provided an opportunity because of AI/ML, and also because of the fact that you can have a lot more functionality on software, you can virtualize a lot of network elements to leverage all of this and try to solve the problem of reaching the remote areas. So now the statement of the solution that we are considering is that these multiple halls have the potential to be designed and deployed flexibly, and this flexibility should be incorporated in the standardization itself, and this can help in mitigating the cost and access challenges and hopefully making it more attractive for the service providers to try and address such markets. And this is something that we want to term as elasticity in RAN. Now, what is the kind of characteristics you expect from this kind of flexible halls in RAN? So essentially what you want is you want dynamically programmable, high capacity, low latency point to multi-point transceivers. So essentially what is going to happen is you could increase the capacity, you could reduce the latency, or you could also handle point to multi-point transceivers, because some of these halls, some of these connections are point to point or point to multi-point as opposed to fully mobile. Then you'll have to work with a software defined cognitive control plane. So cognition is also important and not just being software defined. You have a unified data plane. So you have you're able to support switching architectures. You are able to support switching of architectures as per the requirements of the particular market that you're servicing. So you can, in principle, build network elements which are easily switched between deployments, urban or rural. And as the last point mentions, dynamic deactivation and decommissioning of scarcely used network portions. So all this point and the last point put together means that there is a lot of flexibility in the way the service providers can use the network elements that they procure. There's so this is achieved by reconfigurability and also by the ability to forecast traffic demand in time and space. This is to some extent enabled by this proliferation of AI ML. I'm sorry for that. And all of this should also be easily integrable with future RAN evolution, so that you don't have to reinvent the wheel once you get to the next generation. So if we do all of this right, there is a possibility that we can bring the CapEx and OpEx down to a reasonable level, such that the return of investment becomes, well, at least bearable enough for the service providers. And it is not to say that everything here needs to be reinvented. There are already existing approaches for flexible Hall RANs, but these are largely targeted at existing markets. But now what we should attempt to do is that the open architectures that are being explored and deployed, and the various equipment manufacturer solutions that are becoming popular, what we should try and do is we should try to rationalize them, and we should consciously incorporate requirements of the remote connectivity into the standards that we build for 6G. And just to illustrate what we're talking about, we look at the approach by Keragon, who've sort of looking at 5G solutions where they have some flexibility as far as the halls are concerned. So they call it flexible wireless hauling. And what they're essentially trying to do here is eliminate dependency on fiber. So what you see here is on the leftmost side, you have latency which decreases as you move from the backhaul to front haul capacity, which increases as you do as you make the same move. And also what happens in the middle part of the diagram is disaggregated wireless hauling. So you have you sort of talk of multiple halls to make sure that the payload reaches from the core to the interested user. And finally, because you're able to define it in software, you'd be able to have a lot more flexibility. And this is how we people talk of things right now. You have a backhaul between the core and the centralized unit. You have a mid-haul between the centralized unit and the distributed unit. And then you have a front haul right up to the radio unit. And on the other axis, you have hardware which can be off the shelf, and it could be on the cloud, so which offers you a lot of flexibility. And the software should so evolve that it can manage both proprietary and open software integration. Classically, the hardware, software, and radios are in silos, and it's extremely difficult to deploy. And the article by Keragon also talks about another thing that's very, very interesting. So they talk of 2 axes and 4 quadrants. The axis is the network architecture strategy, which, when we call it disruptive, is when you allow for the hardware to be generic, when you allow for software to be flexibly deployed, and you allow for multiple halls, and these halls can be elastically configured. So if you allow that kind of a disruption in a network architecture strategy. You could have services which are disruptive. You could have services which are classic. So if you look at the two quadrants on the top, there's one which is cost driven, the other which is highly disruptive. So as the standards are evolving, they are focusing more on the first quadrant, highly disruptive. What we're saying is that as 6G evolves, it should not totally overlook the quadrant on the top left, the cost-driven quadrant. And this quadrant is what we are saying is possible to achieve by using disruptive network architecture strategy, but offer services which probably are classic in nature because the remote areas might still be looking for those kind of services. So there are a few potentials for contributing in this area. So these can be summarized as building in support for ultra low mobility in some of the halls. The other thing that we could do is some of these halls could have physical layer specifications as well, not just defining the way the payload can be distributed. Then software-defined network specifications should have built-in within themselves the ability to support the requirements of remote area. We should talk about reconfigurable back to front hauling. And finally, one can also explore hierarchical architecture of these RAN halls, because you have multiple halls going from the CU up to the user equipment. Can this be made hierarchical so that it can be fully exploited? Well, this is all I wanted to talk about. Thank you very much. And I hand it back to you, Hari.
Okay, thank you. Nice presentation why we need this flexibility. So next it's your turn, Chaoub.
Thank you, Hari. Let me just share my slides. So, hello, good morning, good afternoon, good evening, everyone. I'm very glad to have this opportunity to talk about and give some insights about our work on the 6G white paper on remote and rural areas connectivity from the spectrum perspective. So I will start just by talking a little bit about the importance of spectrum. You know that spectrum is the lifeblood of the telecommunication markets. It is one of the major challenges for remote areas connectivity. It is also important to define the term remote area. In our white paper, we refer to remote area as those locations that are either underconnected or unconnected at all. So when we talk about remote area connectivity, we talk about extending connectivity beyond the traditional urban connectivity. And so we are talking also about a strong three-dimensional connectivity. However, the lack of favorable spectrum remains a serious impediment to that kind of connectivity, because the requirement here is no more extreme throughputs, but rather the requirement or the main requirement is coverage. In general, there is two broad options to increase the amount of available spectrum. Either using innovative spectrum sharing, reuse, or optimization models. This topic has great and huge potential, and it is among the hottest research topics today. Or we can also think about introducing new bands like the millimeter and terahertz bands, but the limitation here is the poor coverage and the high path loss. So now I will move to a number of bullets that I have listed or we have listed in our 6G white paper as potential solutions to spectrum availability in the remote and rural areas. So first option or first solution is cognitive radio and coexistence. You know that sub-6 GHz frequencies are very critical to such kind of connectivity, thanks to their favorable propagation conditions, giving wide reach and good penetration. However, such bands are crowded very crowded today, are fully assigned, and it is very hard to free up some of them. On the other hand, in remote and rural areas, the distribution of users is very sparse. And this is very useful because we can have the so-called spectrum holes or white spaces. And those can be leveraged in some bands like TV, radar, or GSM bands to increase spectrum availability and extend connectivity to remote households, but also to more distant locations like farms and wilderness areas. However, we still have some challenges and some research directions. We need accurate radio awareness. We need innovative spectrum sensing, strong geolocation databases, and reliable radio environment maps, more importantly. We need also to take into consideration the unauthorized transmissions. You know that such kind of bands can be the subject of some malicious transmissions from some parties. So we need to take that into consideration because it is just something we cannot predict easily. And finally, we need also to introduce some innovative techniques like parallel sensing and transmission to decrease the complexity at the node. We can, for example, there is many techniques to be able to perform sensing and transmission in parallel using, for example, interference cancellation. The second point is the so-called horizontal and vertical spectrum sharing. So horizontal refers to sharing spectrum by many operators, but with same priority. On the other hand, vertical is sharing the spectrum by many operators or many users, but this time with many and different priorities. So the example here, or the popular example, is the licensed shared access in Europe and spectrum access systems, or CBRS, for example, in US, which are mature enough using 2 tiers and 3 tiers of users respectively. This kind of models encourage us to think in 6G about evolving them to support more users and services vertically, and more operators or incumbents horizontally. Okay, so and when supporting a larger number of incumbents and users, we can decrease the cost of spectrum, but we can also promote local content providers in remote areas, since we have some special services there like farming, mining, and safety, for example, in oceans or in deserts, for example. So the challenges here are mainly interference management and mitigation. You know, when evolving to a higher number of users or layers and higher number of operators, we need to manage the risk of interference among them. We need also to manage databases of various players. Okay, we need also to guarantee quality of experience and quality of service for all the stakeholders. And we need extremely accurate radio environment maps, because such models can be driven by such radio maps, and we need to have as much as accurate. The third point is spectrum aggregation and multi-connectivity scheme. So there is 2 parts here. Spectrum aggregation refers to the situation when we have one source and one destination, but performing their communication on a number of bands or on multiple bands by aggregation. Okay, so this is the so-called carrier aggregation, but in 6G we need to evolve this kind of carrier aggregation to something more advanced by using a larger number of bands, and these bands can be low, mid, or high bands. And such kind of schemes will help obtaining scalable bandwidth. And this helps to maintain service continuity, especially if we lost connectivity on some bands. As you see in the figure at the top right, we see, for example, some vital facilities in rural and remote areas that we can put just in the zone or the cell covered by the combination or the aggregation of those bands, so that if we lose connectivity in some bands, we can still have a high chance to connect those facilities via other bands. So the challenges here are the complexity of the transmitter and receiver circuits, because now we will operate on heterogeneous bands. So this there is hardware complexity that we need to deal with. There is also the need for agile antenna or extremely agile antennas, especially if the gap between the bands is very high. And we need also to think about flexible and enhanced uplink and downlink split. Now, if we have multiple bands and or a larger number of bands, we need to decide dynamically, hopefully, at each frame or each frame about the number of bands used for the uplink and the number and which bands used for the downlink. The sets can be different each time, and this needs to be dynamically managed. Always in this multiple connectivity schemes, now I will talk about multi-connectivity schemes. Instead of having one source, this time we will have multiple sources addressing or sending the same signal to one destination. So this can be also seen as multiple routes sending the same signal to one destination. And when talking about multiple routes, here we can exploit the diversity and pervasiveness of some technologies like Wi-Fi, TV, headnets, etc. And this can be also very useful because, as you see in the figure, we can have scalable aggregation at various either protocol or architecture levels. And this can help obtaining seamless mobility because the user or the UI can move between cells and can always keep connecting to the core, but also can also help obtaining load balancing and fault tolerance, especially in hard to reach areas. The challenges, for example, here are the complexity which is reported at the edge, because now we have more complexity at the UEs and the base station. This is something we need to manage, and we need also to manage to coordinate the resource scheduling between those sources, because we can have, for example, handover, we can have, for example, some directional communication. So we need to manage also beam directions. No, my slides. Okay, sorry. So now I will move up to point number 5, using or utilizing unlicensed bands. So there is a recent trend to release and unleash more and more unlicensed bands. And the idea is to use them just with the licensed bands to increase, for example, capacity or coverage in some locations. It is also suitable to keep an anchor in the licensed bands so that this will increase the reliability of such schemes. The challenges for using the licensed bands are sometimes we need to keep harmonious operation with the lower bands, because higher bands, for example, can have some issues with line of sight. So we need to harmonize the operation between both types of bands. We need also to evolve control and listening mechanisms like LBT. Conventional LBT need to evolve to more cooperative and distributed schemes to avoid misleading spectrum occupancy, because we can have some directional transmissions and some beams, and we need to introduce some innovative detection mechanism to deal with this feature. We need also to manage the uncoordinated competing users, because this is a licensed bands, and we can also have some other technologies that operate on the same bands, and we need to manage the risk of interference between all those players. Finally, there is also an emerging topic, which is optical wireless communication. So especially talking about free space optics or visible light communications, those are two popular examples of optical wireless communications that are gaining high popularity today. The main advantages of such type of spectrum is license-free operation. We don't need license fees. The full duplex mode, huge available spectrum, and robustness against interference. Okay, so from our perspective in the team of remote and area connectivity, we suggest, for example, to use VLCs to boost the throughput in indoor, fronthaul, and underwater environments, and to use FSOs as backhaul solutions in the remote areas, for example, between two mountains to reach a distant location or distant village or a distant maintenance facility, for example. So some research directions here for 6G are, for example, the sensitivity of the transmitter-receiver link to misalignment issues. We need, for optical wireless communications, we need to keep aligned both transmitter and receivers. So this is a constrained feature. We need also to manage handover if we opt for cellular deployments. And we need also, if we opt for an optical wireless communication stack, we need to revisit the protocols at various layers, because now we will have we will need some protocols that are different from their RF counterparts. So now I have reached to the end of my presentation. I would like to conclude with some final remarks. It is obvious that local, flexible, and pluralistic spectrum sharing or licensing could be the way forward to boost the market or the remote market. This can be supported, as suggested by my colleagues just presentation before, by software-defined technology embedded into off-the-shelf multi-vendor hardware. This will increase or decrease the cost, and this have a big potential for digital inclusion. We also encourage stakeholders' cooperation between various players like MNOs, regulators, vendors, and manufacturers to get to those remote locations. Another point, the use of AI and ML techniques can provide cognitive capabilities for, it is a dual objective. One, an optimal use of licensed spectrum, and the other is prudent use of shared spectrum. Spectrum sharing should be expanded to include the higher bands, because higher bands are a little bit special regarding their specific characteristic of high path loss. So we need to address this more to be able to integrate them in the 6G vision for remote areas. And I think the timing is just perfect to unpack to the 6G requirement specifications, such that those proposed and potential solutions can be considered into the design process from the beginning. So I have reached the end of my presentation. Thank you for your attention, and I will be happy to respond to some questions at the end. So back to you, Hari.
Yeah, thank you for explaining the spectrum issues. So now I hand the floor to Adrian, our final speaker. And then we will have this QA session, so we still have room for a few questions, or more than few.
Okay, so how do you see my screen now?
Yes, I can see it.
Okay, so thank you for giving me the floor, and welcome everyone on this final talk on this 6G research webinar series. So as it was introduced by Hari, I will concentrate briefly on the regulatory aspects on this remote rural area connectivity. I came from Poznan University of Technology and I present also research remote labs. As it has been properly identified by my previous speakers, the problem we have now with the remote areas and from other sides also the digital oasis is that there is very low average revenue per area, per user, per unit, whatever. So then there is, as we know that, there is an immediate question, as it was also mentioned previously, who would like to pay for first a spectrum license, who would like to pay for any infrastructure investment. There are different solutions so far, but if we have a goal, if we have a target to really deliver services to the whole world, I mean to every place on earth, in the developing and developed countries. So there are immediate questions if we have tools or enablers that simply allows it. And the question is, on these enablers. Some of them have been mentioned previously. I try to categorize them briefly in three puzzles. So the first enable will be simply the technology. So what do we have? Just to briefly summarize, we have all the solutions coming from dynamic spectrum access schemes, as it was mentioned by Abdelaali. We have this LSA scheme, CBRS scheme. There is a concept of a technology, including also within 3G and 4G, for the concept of private networks. This already exists. We have this multiple operator core networks and the others I will talk about later. So there is some sort of technology. And then if we see on the other domain, on the second domain, we have some regulatory issues. So how we can use the spectrum, what will be the price, and who would like to pay for it. There are also different options. I will present them briefly in a while. And also the third puzzle is the business, simply. So what kind of operator, what kind of business model could be applied to simply get some revenue and to exist on the market? So there are different proposals already. So these are called like micro operators, rural operators. There is an idea to come back to national roaming, and also private networks from the perspectives of business domain. If we look briefly on technology, as Chaoub mentioned previously, we have already such schemes. I focus here on technology, like license shared access and the citizen broadband radio service with SAS. So simply speaking, what we have is that there are some regulations. So there are some incumbent users that they can use spectrum, but there is also some kind of controller, some kind of database. And then we can try to use the existing resources in intelligent way. This is particularly important in these remote areas because these oases are really the oases very often, or we have very hard access to these areas. So the big players may not be that interested in that model. So maybe we should focus rather on smaller players. And in that case, there should be a way, that technical way, that these smaller players can use the spectrum, which is normally licensed to the others. So there are two technologies that exist now and they work fine. So one is LSA and CBRS. Also, there are many others, like mentioned previously, but these we can treat as some existing technical enablers. Then also what we have now quite widely applied, there are different kind of sharing. So of course, when we imagine that there is even that there is some infrastructure investment and we have a site installed somewhere, I am focusing now on something installed on the ground. If there is a site, then of course, if there will be other player, let's say micro operator, then it would be without sense to install to make new infrastructure investment. So it means that such schemes like site sharing, which is very popular also nowadays, or different schemes like this multiple operator radio access network, where the frequencies are split and not shared, but the radio access is shared, or this multiple operator core network, where the core networks are just not shared. So these are the techniques which are already standardized in 3GPP documents. So we see that it happened that it works quite well. So appropriately tailored such schemes, including this LSA and CBRS as examples, these simply are technologies which exist and could allow for efficient spectrum sharing, so deliver some resources to this remote area that can be used by the smaller players. If we look on some examples, if we concentrate on the regulatory decisions, these are just 6 selected examples. There are many others which can be found around our globe. So as I mentioned, the CBRS is probably one of the most well developed, meaning that there are a lot of investment in the US and business deployment. So what we can see in the US, there is a 3.5 gigahertz devoted mainly for CBRS. In Europe, we are concentrating more on LSA and this band. What is important, for example, in Germany in 2019, he relaxed this 3.5 to 3.7, 3.8 gigahertz band for private 5G networks, and it was quite a big success. Then in France, there is also private public usage for 2.6 gigahertz. In UK, they focused previously a lot on TV white spaces, but also on this LSA schemes. In Finland, of course, Australia, Japan, and many others. So these activities are ongoing. So we can see that regulators coming from different countries, they also see the need in changing the regulations simply to allow such operating schemes. But also regulation is just one hand. On the second hand, we have money, of course. So if we have to change the regulations, then the immediate question is how we can get money from it, how it will be fair to use the spectrum. So what is on the table? What is proposed? So we have two extremes. On the left side, we have, which is popular now, license access, where of course the fee mainly for the spectrum and now also for the infrastructure is paid by MNO or some mobile network operator. The advantage of it is simply that we have control interference. There is no need for any sensing, so we have spectrum for us. So exclusive use of spectrum, and the quality is usually very high. On the opposite side, which is also very popular, is opportunistic access. So VLAN-like services when there is no fee or very low fee. But of course, the cost of it is simply interference, as we know from our everyday practice. There is a need for sensing if there is someone else using this spectrum. So this is some kind of spectrum sharing. And the quality of service or experience may be very low. But as I said, these are two extremes. And in between, we have a plethora of different, schemes that could be applied. These are known in research area as pluralistic licensing, when simply we can reduce a bit from the license access or give more control to opportunistic access, and we have different solutions. So this is the way that could follow, and also that could provide some benefit to the regulator. And the Germany example is quite an interesting one, because I just see recently the announcement that they stated simply that this experience with this 3.7 gigahertz band, it was quite successful. And the interest of the private networks, so they have small amount of money devoted for spectrum for time-limited licenses. It was simply working well, so they would like to continue it. And then, so these are we have these technical neighbors for the spectrum mainly. We have this licensing options and regulatory decisions, which are now ongoing. And then, what are the models that can be applied for such areas like this digital oasis, this remote areas? Of course, here what we see on the left side, we have a local micro operator. So the operators which are offering dedicated services solutions for some specific areas. In our case, it will fit very well. So we can say about location dependent or tenant dependent applications. So micro operators that offer some services for a given area or for a given customer. For that, we need this time-limited and maybe location-limited licenses. But also, there are other options like services tailored to other operators, mobile network operators, but only at a given location. So there are two approaches that if we look on the left side, we have some application provider, network infrastructure, which it does not need to be the micro operator itself. It can be, let's say, private, public, scheme where the community is making some investment in the infrastructure. So the local operator will be really somehow limited geographically. But also we may have a situation where simply there is a mobile network operator that simply offers some resources to local micro operator. And any hybrid scheme that gets some benefits from the left on the right side model are also applicable. So local micro operator that offers its services to some remote areas, it's a good solution. And also this regulatory aspect, they simply support it. And finally, there is a concept of national roaming. So simply if we have a SIM card, what we have now is that typically we can use the network which is managed by one mobile network operator. Very often regulators prohibit to use this national roaming because to prevent for example, from creating of some cartels and so on. But in such cases, like in such places like this remote areas, it will work quite well. So there is also the need to rethink or redefinition of this national roaming for such application. So if we summarize this, we may say that this puzzle can bind together. So we have already the technology. We have some already. We already have some regulatory decisions. We have some proposal of business models, and such models exist, as we have private networks in Germany and other places as well. So these could be the technical enablers for this remote area connectivity. So thank you for this brief introduction on this regulatory aspect. I give the floor to Ari.
Yeah, thank you explaining that there is other things than technique that we have to solve. So that was all our presentation, and we basically went through the white paper, what is available in 6G channel. And now we check the questions and give answers to them. I think we have 10 minutes left, but only 7 questions. Can you panelists see the questions?
I can see. I can answer because do we answer now or immediately or
yeah, now,
will be the procedure?
Yes, I can.
I can just answer one by Sarat, which is how we will differentiate between mobile network operator and local. So simply speaking, I would say that mobile network operator will be the stakeholder that offer the services to a very broad geographical area, and local is simply devoted to simply small geographical area. And there are different ways how we can do this, but if we see on such schemes like Open RAN and solutions like that, can quite easily deliver radio resources and our services to local community.
Okay. Any other views for that question?
Hari, I can respond to the second question. Yeah.
Okay, please. Oh, maybe we have to read the question.
Yes.
So question, I'm interested in where and how much quality communication services are available using 6G. For example, do you think we can use the same data rate services in urban and rural area? I would like to know how effective non-terrestrial networks are in solving the digital divide problem. Please, Chaoub.
Yes. So in our white paper, but also in some other surveys in literature, we are talking about specific grades for remote areas connectivity. You know, now we have the 3 classes of services, URLLC, EMBB, and MMTC. But the vision now, there is like a common belief that we need a 4th service grade for these remote areas. And so when we talk about 4th service grade, we are talking also about the corresponding KPIs. And among the KPIs, certainly we don't have high throughput or high peak rate of 1 terabit per second. We're talking about something like 1 megabit to 10 megabits per second as throughput, because the challenge there is a little bit tricky. I think from a network perspective, from an infrastructure perspective, the main challenge is backhaul, right? So and we addressed in the white paper many possibilities for the backhaul, and also Professor Alouini talked about some of them in his talk today. We are mainly thinking about, for example, free space optics or satellites. These two solutions are very popular now for remote areas. So let me just mention that free space optics, for example, can be very efficient. For example, we can put them into on the top of mountains, or and just we need just to be sure that we have the alignment between the transmitter and receiver, and we can have good backhaul to remote areas. So this is it. So if we need a fourth or another class of services with very specific KPIs, moderate throughput, but we need to focus rather on the coverage, because the challenge there is the coverage and not the throughput.
Yeah, Hari,
Thank you.
it seems there are a few questions that are addressed to me. If you want, I can take them anytime you want.
Yes, I think now it's time. It's next
Okay.
on. Oh,
Okay.
yeah. Do I read the
Thanks.
questions? Yes.
There are 3 questions. I can try to summarize them quickly. One from Mariam Lasghari, who's asking question about the challenge to use optical fiber as backhaul for UAV and balloons, and then the challenge if you want to kind of have a functional split. So obviously, you can of course use optical fiber for backhaul if it happens that basically optical fiber can make you reach an area close to a remote area, like an area where there is enough density population and that there is still a good business to dig and put fiber optic. But then after a certain limit, you start having some sparsely populated remote region. You can definitely make the fiber reach the edge of that area and then put your balloon or your tether UAV there and get this extra 50 kilometer, 1 kilometer of coverage towards the rural area. So that this combination is possible, like the combination if you're in the middle of pretty much nowhere, that the backhaul in that case have to be done through satellite. Question number 2, can you have this functional split? Of course, because of course tether UAV or tether balloon have definitely an advantage in comparison to a standard kind of like untethered UAV, in the sense that it can have a heavier payload. I mean, some of these balloons can carry up to 250 kilogram in the air, but still you want to do as much saving as possible, because, you know, if you save a little bit on the processing and you can put it on the ground, then you can put more antenna, you can go for an 8 MIMO or 16 MIMO on the air, more RF chain on the air. So the more saving you do, the better it is. So definitely there is nothing wrong about having this functional split, where basically some of the kind of RF front end is in the balloon and some of the baseband processing is done on the ground station on the ground, where there is actually also the power and there is no payload lift issues. That's, I think, to address Mariam Lasghari question. Question number 2 from Mr. Anuj Agrawal. And the question is, let's suppose that fiber and satellite will have equal capex and opex in the future. What will be the better technology for backhaul in terms of capacity, latency, and carbon footprint? So, I mean, to a certain extent, I mean, I think it's clear to all of us that if you are operating in an environment where there is enough density population, then the fiber optics is the way to go. But it's just really difficult. So what I'm trying to say, you can start with an environment with this sparse population where basically there is no way that you can match the cost that broad cover satellite can provide. So basically you cannot equate the capex, opex kind of expenses in that kind of let's say sparse populated environment. But at some point, if that kind of area becomes more populated and there is enough traffic, then of course, then, you know, like the fiber becomes the solution to go. But in general, when you are dealing with a sparsely populated environment, I think no one can, I mean, you cannot beat like an aerial solution for backhaul, because it's possible to send fiber to everyone, even actually in kind of urban area, let alone in remote, difficult terrain, difficult to dig areas in sparsely populated regions. So that's my answer to question number 2. The last question, the thing that is addressed to me, is, do you see the LEO satellite with global constellation to cover the whole world solve the problem of remote connectivity? Is this research on satellite-based front haul with RUs? Okay, so I mean, I think my answer to that is, first of all, I don't think there is a single satellite solution. As I mentioned, within time limitation, I could not dig more, but you have different solutions. We have the LEO constellation. There is a new generation of very high throughput satellites with multi-beam capabilities. There is also this kind of low-cost mini geo satellites. So there are many families of satellite solution. Collectively, I think down the road, they will offer really this kind of a global connectivity kind of solution. Like, as you know, for example, one of the aspects of current satellite is that they cannot cover the poles, like the North Pole and South Pole and regions around that. With basically LEO satellite, will be able to overcome that. But the problem is the cost is still high. The investment to get this off the ground is still quite expensive, and that's why you have the giant like SpaceX and Amazon feeling that there is a need, there is a potential from a business perspective to connect the world, and these are the kind of really big part of investing. But I would say in between now to 10 years, 15 years down the road, when this baby mega constellation will become a reality, I think the solution based on tether balloon, on these aerial platforms, like HAPS, can be a good kind of bridge to reach this kind of LEO mega constellation, become cost effective and becoming really kind of the way to connect the world, at least from backhaul perspective. Thank you.
Thank you. I think next one from Sachi is to allow Chaoub. What is the difference between MNO and local micro operator? Do you want to answer, or shall I try?
Yes, I can give some insights into this question. So the difference is that mobile network operators are the conventional operators that are operating in bigger location. And now the main problem with the remote areas connectivity is that the conventional operators are not very interested in getting to those remote locations to give connectivity there, because the business model from their perspective is not profitable, right? And so the new business model now is to create some kind of local operators or micro operators that can be some local service providers, or but they can operate locally, just locally, and for example, can lease or can get backhaul from those MNOs. You see, so there is this is the difference. MNOs are the mobile network operators that are conventionally or operating in the telecom market now, not interested in getting to remote areas because the business model is not good from their perspective. And there is the new notion of local or micro operators, some kind of small operators that can start just operating in locally and providing services, sometimes very special services to remote and rural areas. And the business model is profitable for them because they don't need to deploy the whole infrastructure. They can just lease a part from the MNOs and just deploy smaller parts in the remote and rural areas.
Okay. And I think the next one also goes to you, Chaoub. Optical wireless communication. Is optical wireless communication getting serious consideration for 6G? If yes, what would be the best place for standard development, IEEE or 3GPP?
Yes. Optical wireless communication is an emerging topic today and very promising. there is many attractive features there. There is the free, the low cost or the free fees model of this kind of spectrum. There is also the full mode, which is more simple than in RF, and there is also the available spectrum, which is high and considerable. The challenges are just some specific characteristic of light transmission. As I said in my brief presentation, we need to keep this alignment between the transmitter and the receiver, and in very dynamic environment, we need to take that into consideration, just like it is just similar to the higher bands in RF. For example, for millimeter or terahertz bands, we need to keep to do beam sweeping, beam tracking, beam scanning. We need to be always like aligned with the transmitter to keep receiving the beam and the high power. It is similar in optical wireless communications. We need to keep alignment because light, because of the light transmission characteristics. And what is the appropriate standard? I really don't have a preference. We can have 3GPP and we can have IEEE. But what matters is the advantages, but also the limitations that we need to deal with to have this type of spectrum very candidate or potential candidate for 6G networks.
Okay, thank you, Chaoub. I think that was all the questions what we got. So I would like to thank all panelists and our audience for this event. It was nice to show our results. And I have few announcements here before we finish. So first is that these 6G research vision webinars will continue. In next week, we will have about machine learning in 6G white paper. And 21st of October, it's about edge intelligence white paper. And then there will be several more during this autumn. And second thing that might of interest to you is that we are preparing special issue proposals, and you stay tuned on 6G channel and other channels, so you will see when those will be available. And that ends my part of the seminar. Thank you, fellows.
Thank you, Hari. Thank you, everyone.
Thank you, Harry. Thank you, everyone.